This is the video assignment solution given by Sir Mohit Guttu of Mechanics. I have been assigned a question from Dynamics, chapter number 3, question number 193. The question is as follows. The space shuttle launches an 800 kg satellite by ejecting it from the cargo bay as shown. The ejection mechanism is activated and is in contact with the satellite for 4 seconds to give it a velocity of 0.3 meter per second in the z direction relative to the shuttle. The mass of the shuttle is 90 mg. Determine the component of velocity Vf of the shuttle in the minus z direction resulting from the ejection. Also find the time average FAV of the ejection force. So according to the given question, we have to find the final velocity of the space shuttle after the impulse and also the average force imparted by the ejection. So let's get to the solution of the question. Let Vf be the final velocity of shuttle resulting after ejection and V1 be the velocity of satellite. As we can see in the diagram, V1 is in positive z direction and Vf is in the negative z direction. Since the velocity of the satellite relative to the shuttle is 0.3 meter per second, according to the relative velocity concept, we have an equation Vf plus V1 equal to 0.3 meter per second. Since there is no external force as given in the question and it is in complete space, we can apply the conservation of linear momentum in the system. As the conservation of linear momentum is m1v1 equal to m2v2, the momentum is conserved, we get mv1 equal to m0 v final, where m is the mass of satellite and m0 is the mass of space shuttle. Keeping the values, we get a relation that V1 equal to 112.5 times Vs. Now putting this equation in the equation of relative velocity we got in equation 1, we get the final velocity as 0.00264 meter per second. Now we get to the second part of the question. In the second part of the question, we are required to find the average ejection force, that is, the impulse put on the space shuttle by this ejection of the satellite. According to the definition of impulse, a large amount of force in a short period of time is equal to the change in momentum, which is the impulse. So we make use of the equation derived from the second law of motion by Newton, that is integration FTT equal to change in momentum. So by using the equation FAV integrating dt from 0 to 4 seconds is equal to m0 into Vf, since we are calculating with respect to the space shuttle to use the mass of the space shuttle. Putting in the values, we get the final force average equal to 59.4 Newton. That is all the solution of the question. Thank you.